Hey everyone, and welcome to your ultimate introductory astronomy exam crash course. Look, if you're feeling a little overwhelmed by the sheer vastness of the universe right now, or, just the vastness of your textbook, you are absolutely in the right place. Today, we're going to take some of the most fascinating cosmic theories ever conceived and turn them into a high-yield, super clear study guide. By the end of this explainer, you're going to have a rock-solid grasp on the search for extraterrestrial intelligence, the actual mathematical odds of alien life, and the, quite frankly, terrifying reasons why our universe seems so incredibly quiet. So, get your notebooks ready because mastering this is going to guarantee you ace your test. All right, let's just dive straight into the syllabus. Here's your study checklist for today. We'll start with 20th century cosmic discoveries, define the Fermi Paradox, break down the Drake equation variables, trace the evolution of Seti, and finally, compare the rare Earth hypothesis with the dark forest theory.
So kicking things off with Module 1, 20th Century Cosmic Discoveries, or Deprovincializing Our Worldview. Let's set the stage here.
The great astronomer Carl Sagan actually called this the deprovincialization of our worldview. Definitely write that vocabulary word down for the exam. Basically, step by step over the centuries, science proved there is absolutely nothing geographically special about Earth. I mean, think about it. In the 16th century, we finally figured out we aren't the center of the solar system. By the 17th, we realized those little points of light in the night sky, they're just other suns. In the 19th century, we discovered our planet has this deep geological age that vastly predates human history. And then in the 20th century, we looked through our telescopes and realized those blurry spiral nebulae were actually entirely separate galaxies, just like our Milky Way.
And that realization brings us to this frankly staggering number, 2 trillion, as in 2 trillion galaxies in the observable universe, with some of them containing up to 1 trillion stars each. Because science proved Earth isn't in some sort of unique, privileged location, scientists logically concluded that the ingredients for life literally must be everywhere. The universe is incredibly large and incredibly ancient. We're talking roughly 14 billion years old. So, statistically speaking, we shouldn't be the only ones here.
Moving right along to Module 2, defining the Fermi Paradox, the ultimate question. And what's really fun about this is how a completely casual 1950 lunch conversation basically created the biggest problem in modern astronomy.
Picture this. It's 1950 at the Los Alamos National Laboratory. Famed Italian-American physicist Enrico Fermi is just walking the lunch with some colleagues, including Edward Teller and Emil Konopinski. They'd just been laughing about a newspaper cartoon showing aliens stealing New York City trash cans. Well, they sit down in the cafeteria, and out of nowhere, Fermi looks at his colleagues and asks this profound question: where is everybody? They laughed, but they knew exactly what he was getting at. You will absolutely see this quote on your exam.
Okay, definitely jot down this core definition for the test. The Fermi paradox is that severe conflict between the high mathematical probability that intelligent extraterrestrial life exists and the total lack of conclusive evidence that it's ever actually arisen. Think about it. If the universe is teeming with stars and life naturally expands to fill available niches, why haven't we seen a single verified spacecraft, probe, or even a stray radio transmission? Even traveling at sub-light speeds, a civilization could theoretically colonize the whole Milky Way in maybe 5 to 50 million years, which is just a blink of an eye on a cosmological scale. So seriously, where are they?
So, how do we actually calculate those odds? Let's jump into Module 3, the Drake equation variables.
You'll want to memorize these variables. Back in 1961, astronomer Frank Drake came up with this equation to calculate n, which is the estimated number of technologically advanced civilizations currently hanging out in our galaxy. It's brilliant because it perfectly structures our ignorance. It systematically breaks the problem down, starting with the easiest astronomical variables at the top and working down to the incredibly hard sociological variables at the bottom. We start with R star, the rate of star formation, which we actually have a pretty good handle on today. Then we look at the fraction of those stars with planets and the number of those planets suitable for life. But here's the catch. As we move down that list, the fraction where life actually appears, then intelligent life, then life capable of transmitting signals, and finally L, the length of time a civilization survives before, well, destroying itself, it basically becomes pure guesswork.
Now that we've got the math down, let's look at the practical side of things in Module 4, the evolution of Seti, or humanity's search for answers.
So Seti, the search for extraterrestrial intelligence, actually has a really quirky history, evolving from some wild 19th century ideas into modern astronomy. In 1820, mathematician Carl Friedrich Gauss seriously proposed drawing a massive petroglyph of a right triangle on the Earth,
like huge enough to be seen from the Moon or Mars, just to prove to the universe that we understood geometry. By 1899, Nikola Tesla conducted what might be the first passive Seti experiment, picking up these inconclusive radio signals he thought might be coming from Mars. Fast forward to 1924, and there was a literal National Radio Silence Day, where citizens were asked to turn off their radios for 5 minutes every hour to clear the airways so scientists could listen for Martians. But it wasn't really until 1960 that the true scientific discipline of SETI began, with the first dedicated radio telescope experiment listing specifically for transmissions from other star systems.
But here's the thing. Despite decades of listening, we've heard absolutely nothing. Why? Well, that brings us to Module 5, the Rare Earth Hypothesis, a biological filter, which was published by Warden Brownlee back in 2000.
If this pops up on the test, just remember that the Rare Earth Hypothesis totally pushes back against the idea that our planet is typical. It argues that sure, simple bacteria might be super common in the universe, but complex life? That requires a massive, massive list of fortuitous, highly improbable physical circumstances. You don't just need a planet in the habitable zone of a star, you need to be in the safe zone of the galaxy itself. You need a gas giant guardian, kind of like our Jupiter, to sweep up life-ending asteroids. You need a massive moon to stabilize the planet's climate. You even need plate tectonics. So according to this theory, Earth isn't just average, it's a wildly lucky cosmic lottery ticket.
And all those crazy improbable requirements? They introduce what we call a great filter, a term coined by Robin Hanson in 1996. The great filter is basically an evolutionary barrier, maybe biological, maybe technological, that is so exceptionally difficult to pass that almost no species actually manages it. The Rare Earth Hypothesis suggests the great filter is already behind us, like maybe the leap from simple single-celled organisms to complex eukaryotic cells was just an incredibly rare freak accident. If that's true, the universe might be completely filled with simple slime, but almost entirely devoid of actual intelligence.
All right, finally, let's explore Module 6, the dark forest theory, a sociological filter. Because what if the great filter isn't biological at all? Let's look at a terrifying alternative popularized by Lou Sixson's 2008 sci-fi novel. Listen up, because this sets up the absolute perfect essay question contrast for your exam. The Rare Earth Hypothesis is a biological filter saying life is physically rare. We hear nothing because there's literally no one out there to speak. But the dark forest theory, that is a survival filter. It says that intelligent life does exist, and it might even be everywhere. However, they are staying completely silent on purpose. Why? Because in a universe of limited resources, any other expanding civilization is a massive potential threat to your own survival. This whole chilling concept is captured perfectly by Lou Sixson. He wrote, "The universe is a dark forest. Every civilization is an armed hunter, stalking through the trees like a ghost. If he finds other life, there's only one thing he can do: open fire." In this framework, the silence of the night sky isn't the peaceful silence of an empty graveyard, it's the tense, terrified silence of hunters hiding in the brush. It leaves us with this heavy thought: making yourself known to the cosmos, like through our active SETI radio broadcasts, well, it isn't a friendly wave to a neighbor. It's a flare inviting a paranoid, hyper-advanced predator to violently destroy you. So as you review these notes tonight, ask yourself this final question. When you sit down for your test, and you have to answer Fermi's ultimate question, where is everybody? Which side of the evidence do you find more compelling? Are we an impossibly rare biological miracle, sitting safely alone in the dark? Or are we just a dangerously loud, naive target in a very quiet, very hostile forest? Keep that question in the back of your mind. Master these theories, and I know for sure you are going to do fantastic on your astronomy exam. Happy studying.